Let's go from current slide. Okay. Few announcements, not very many and not very important probably. I don't know if you're interested in this because you're a transient student, right? Okay, what, UAV or? UAV, okay. Friday, day after tomorrow, at 10 o'clock in the morning, on the Birmingham East Campus, in the A.G. Gaston Auditorium, I think it's UAV's theater department is putting on a production of Shakespeare's Taming of the Shrew. Now, they've modified it. It seems like people can't stand to do original things anymore. They have to make it more creative or something. But anyway, I'm sure it's still good. Taming of the Shrew is a comedy, one of Shakespeare's probably more famous comedies. And the story was, I don't know, I've never read it, but I've just heard about it. There was this woman who was very strong-willed and opinionated and this kind of stuff. And this guy either was supposed to marry her or whatever. And anyway, he was going to tame her. And that's the whole, battle, and it's supposed to be really, really funny. In Shakespeare's time, I think it was, just groundbreaking probably. Okay, don't know that for sure, but yes. But, of course, rather than mess with a good thing, they do mess with a good thing. And they turn it around, so the guy's a really difficult one, and the woman's trying to tame him. That's what UAV's production is doing. And that's going to be Friday morning, 10 o'clock, the Lawson State campus on the East Campus in the A.G. Gaston building. And then, all right, the other announcements I was going to make. Normally I have office hours today and every Monday and Wednesday from 3:15 to 5:15. My vehicle messed up on me driving in Monday. I couldn't tell what it was, but it was something wrong with it. I got off the expressway and it died. And I got it started again and left on the campus and parked it and then, been trying to get someone to work on it. Finally got it down to Pep Boys, and they had it all day yesterday. They said it was a radiator hose leak. Well, unfortunately, it was right at the bottom, so all the liquid had gone out. And evidently, the engine overheated. The indicators never came on. And the only indicator that came on was the traction control. That's the only indicator that came on. And it came on, and I was driving on a dry road, not braking, so there was no traction control problem. I thought, what is going on here? But anyway, so they got the hoses fixed and filled it up with antifreeze, and now the spark plugs are leaking antifreeze, which is not a good thing. So the head is messed up. And the car is 2010, so it's 7 years old, and it has over 100,000 miles on it. So I don't think it's worth fixing. But I've somehow got to get it from there. I drove it there, and now they say it won't drive. So I don't know what has happened since then, except they repaired the hoses, and now antifreeze is coming out with spark plugs. So I guess there was no antifreeze to come out because it had leaked out. And I do not know. So I've got to figure out what to do this afternoon. I've got to get it off of their lot. And so I'll probably be tied up with that most of the afternoon. So I probably won't be in the office that much. I'll be in there some, but I don't know when. I don't know how long. And I don't know what I'm going to do with the vehicle. I think we're going to have to get a new vehicle, and that's going to take probably the weekend doing that. So probably longer than that. I don't know. So anyway, I don't know what my office hours are going to be today because I'm going to be here, there, and everywhere. Okay. The rest of it, we were scheduled to have a meeting on Friday, but there's been no announcement about it, so I don't know if that's going to happen or not. So anyway, go from there. Any questions on anything we've done here so far? Okay. All right, we were on example 5, an elliptic paraboloid. Okay? says sketch the contour map of f of x. I'm going to blow this up so you can see. Yuck. Yuck. This thing is doing whatever it wants to do, which is not what I'm telling it to do. Okay, let's try it again. Okay, finally. Okay, I can't do a great picture of it, but there's the best I can do of trying not to cut off here or there, but cut off a little bit there. Okay, here's your elliptic paraboloid. This is f of x is equal to x squared plus 3y squared. Okay? X squared plus 3y squared. Now, why is that an elliptic paraboloid? Because when z is a constant, that's your f of x, y, these are parabolas. I mean, ellipses, right? Major axis on y, major axis on x, and minor axis on y. Make sure that's right. Let's say when alpha is equal to, say, 1. Oh, let's make it 9. This is 9. Then you would have divide both sides by, I'll make it 3. Alpha b is equal to 3. C is equal to 3. This would be x squared over 3 plus y squared is equal to 1. That's our standard kind of way it would look. And the y is equal to 0, then x would be equal to 1. So that would be somewhere here, here. And when x is equal to 0, and y is equal to 0, it would be 1/3. Okay, we'll take your word for it that you got it drawn right. But anyway, you get ellipses this way, and if you set y is equal to 0, you get parabolas this way, and when you set x equal to 0, you get parabolas this way. Okay? So that's an elliptic paraboloid. Okay? Now, it says that is the graph of it, so they drew it for us. It says sketch the contour map of it. So how we'll do the contour map, and we'll just take their word for it. We'll let c equal 0, and when c, in other words, your c is your f, that's your z. When c is equal to 0, this x and y have to be 0 too. So you're right at the origin, that's the only plot you have. When you go up to c is equal to 10, or alpha is equal to 10, that would be this circle here, you'd have x squared plus 3y squared is equal to 10, and that would be, say, when y is equal to 0, you'd have x equal to square root of 10, and when you have y is equal to 0, x equal to 0, you'd have y is equal to square root of 10/3, okay, which would be a lot less. So that would be, yeah, there's your ellipse then. When you go up to 20, then you're further out, 10, 20, 30, 0, 10, 20, 30, 40, 50. Now, so these are your your ellipses as you go up the paraboloid, okay? 10, 20, 30, 40, 50. These are the projection down from those ellipses. Okay? It says, comment on the spacing of the contour curves. What appears to be happening to the spacing of the contour curves here? What appears to be happening to the spacing on the contour curves as C goes greater and greater and greater. They're getting closer and closer together, because a paraboloid is sort of broad at the base, but then the higher up you go, the straighter the line, so the steeper they are. So that's exactly it. They're getting closer together because they're steeper and steeper as you go up. Now, that's about the only thing I can think of saying with it. They do mention the thing, of course, that C cannot be negative, because these are always positive, and you're adding two positive things together. So as low as you can go is 0. All right. Now the next one is sketch the contour map. They, thank goodness, have sketched it and the contour map for us of the hyperbolic paraboloid. And that's G is equal to, now I don't see it anywhere on here, do you? Oh, there it is. There it is. Okay. Can't get it all on here. Let's see if I can improve that some. Okay. No, I can't. I was going to see if I can get a little bit better illustration here. Okay. Not a lot better, but a little bit. G of xy is equal to x squared minus 3y squared. Just put a minus sign in there. And again, they did contour intervals 10. All right, now, so that's your thing. Let's go up here and see the graph of this thing. They sometimes call this a saddle point. You can imagine the horse being under here and your legs straight from either side that way. Okay, so that's the saddle point. Now, it'll be hard seeing this and going back and forth between your function, but let's no. Oops. Okay. All right. When you do G is equal to 0, okay, what you have is a you would have a hyperbola there. When Z is equal to 0, you have an hyperbola. And I'm trying to see where that is. Okay. So if this were 0, this would be, well, actually, if Z were 0, then x squared would equal 3y squared. Okay? So in other words, x would be plus or minus the square root of 3y. Right? Okay? And if you had that, that would be two straight lines. And that's one of them here and one of them there. I don't feel like this is drawn properly to scale. It looks like they put them right on the diagonals here. And I think they're supposed to be shifted just a little bit, probably this way. But it's okay. I mean, they've got it all right. Okay, now, if you go up some and positive here, that means x squared has to be greater than 3y squared. And the larger this value is, the greater the difference there. Okay? When you go negative on on G, that means 3y squared has to be greater than x squared. So that winds up being negative. Okay? Now, and again, they're going to do contour intervals of 10, and 10's going up and 10's going there. Now, let's go back up and see why this is called an hyperbolic paraboloid. Okay, the hyperbolic part is any z equals some value here, you have hyperbole here. Okay, like this. And for negative ones, it's sort of hard to see now. They're like this. Okay, coming out this way. Two cross lines here, there, and there, at z is equal to 0. Okay, but you have hyperbole on your level surfaces, your horizontal traces. Okay. Now, why is it called a paraboloid? Well, if you look from this way, vertical traces this way, you have parabolae like this and like this. But if you look, those are opening downward, look this way and your parabolae are opening upward. Okay? Same on the back side, but you don't see that so much. So down here, they're opening upward. You just can't see them over here. There's one there, parts of one. Call this mass. So yeah, it's paraboloid because you got a parabola either way there. And how you see the paraboloid in the figure, say when y is 0, then this is a parabola. Z is equal to x squared, and that would be the one. Y is 0, it's there. That would be that first one. I don't know. Yuck! Hit the wrong key. Okay. Let's go back to, sorry about this. Okay. When y is equal to 0, that would be in the xz plane here. That would be this parabola right there. C is equal to x squared. Okay. Now I'll go down. Hit the right key this time. Oops, too much. Okay. When x is equal to 0, you have a parabola that has a negative coefficient a there. So that's opening down. G is equal to G or Z is equal to minus y squared. Okay, where would that be? All right. When x is equal to 0, you're in the yz plane here, and this would be the parabola. I think this is it, going up here and then going down somewhere over there. It gets all hidden and messed up in there, but those would be parabolas there. Those downward parabolas go like this. The upward parabolas go like this. You know, they fall off like that. Okay, so what are the contour lines like? Okay, again, you're doing your horizontal traces, and when you're going up, nothing over here shows along the y-axis or x-axis or minus y-axis. Everything that you see is on the x-axis. And this is, these are the contours there. With positive x's, this is x or c is equal to 0, c is equal to 10. There's a hyperbola. Hyperbola. 20 would be there, 30 would be there. Okay? When you're going down, minus 10 would be here, minus 20 would be here, minus 30 would be here. Now you're doing these that are cutting away going down. Here would be so hard to see here. There's the crisscross lines here, up here and here. Okay, that's this line here and this line here. And then as you go up, these are the hyperbole, like this and like this and that, going down there around this way, going back into the board. I can't draw it into the board this way, that way. So that's what they was like. So that was with intervals of 10. Okay? For C not equal to 0, the level curve is a hyperbola. For C equal to 0 is two lines, y, x equal plus or minus 3, square root of 3y. And then they go from there. Okay, then I think the next is example 7. And that's not shown here, I don't think. No, maybe it is. I think that is this one here. So let's see if we can zoom in on this one. Okay. Sketch the graph of f of xy is equal to 12 minus 2x minus 3y. Yeah. F of xy is equal to 12 minus 2x minus 3y. Okay? And the associated contour map with a contour interval of m equal 4. Okay? So, what do we have here? Best way to approach this, I think, is first set z is equal to 0. So now you're in the xy plane down here. Okay? There's the very dim in there, but there's the xy plane. Okay? And so this equals 0. Then you can move this over here. You have 2x plus 3y is equal to 12. Well, that would be, on the xy plane, though, 2x plus 3y is equal to 12. If x were equal to 0, y would equal 4. Y is equal to 0, x equals 6. Okay? So that would be this line right here in the xy plane. 2x plus 3y is equal to 12. That's that line in the xy plane here. This line is sort of slicing into the board like that. Okay, well let's pick another. Say x equals 0. Now you're in the yz plane. Okay, so if x is 0, you have 3y plus z is equal to 12. X is equal to 0. 3y plus z is equal to 12. Well, again, we know that when z is equal to 0, your y is equal to 4. We already determined that one. But when y is equal to 0, z would be 12. So that identifies this, and you can do it the other way and let the xz plane let y equal 0. And then you would have 2x plus y is equal to 0, 6, 0, and 0, 6 would be, 0, 12 would be that. So this is a plane. This is the graph of a plane. And that plane cuts through this is just showing the first quadrant pretty much of the, so a little bit in the other quadrants as well, of the thing. This plane is cutting through it's not going to be a good representation, but it would be cutting through, if this was the XYZ axis here, it's a plane that cuts up like that, okay? And so it would have, an X, a Y, and a Z value here. And that would be about how it does, sort of sloping backward, cutting it into a triangle there, but it's an entire plane. So what are its contours? Well, obviously, when C is equal to 0, you have this one right here. And that's this line right here. C is equal to 0. And C is equal to 4, you're up here. And that would be this line here. Okay? C is equal to 4 would be that line. C is equal to 8 would be this line. That would be this one. And C is equal to 12 would be there, and it only goes through Z axis, C is equal to 12. Okay. Yes, ma'am.
It's working now.
It is working.
Yes, I don't know what happened, we just have a bad day Monday.
Yeah, I guess so.
Yeah, but it's working.
Monday got it, yeah, rainy days and Mondays got it down. Yeah,
That's
okay,
right.
right. Okay. All right, so, and it just keeps on going. So these are the contour lines. They're all parallel lines, because, I mean, they're in the whole plane. They intersect the XY plane here, the XZ plane here, and the YZ plane there. Of course, this is elevated up, but those are the contour lines there, okay? And basically what you do, you just set this at different values. When this is at 4, then you have 2x plus 3y is equal to minus 8, okay? Yeah. No, move that way. Is equal to 8. And 2x plus 3y is equal to 8 would be this here. And 2x plus 3y when c is equal to 8, then that would equal to 4. 2x plus 3y is equal to 4. That would be that line. And 2x plus 3y is equal to 12 would be that line. And they just keep on going up. Okay. I don't know why they do such a big deal about this. We don't really use this much, but they're just wanting you to see it, I guess. All right, here's the next one. Okay, this is more of a real life type problem, not sort of a made up math problem. This is actually Mount Whitney Range in California. Does the name Mount Whitney ring a bell to you? Any special meaning there? Mount Whitney used to be the tallest mountain in America, in USA.
Oh, really?
Yeah. Until Alaska became a state.
Oh, yeah.
When Alaska became a state, then it became the second tallest. Well, it may not even be second, but Mount McKinley became the tallest mountain. So that's in Alaska. This is the Mount Whitney Range in California, and that center one there, the tallest one there, is Mount Whitney. But you notice there's a whole range of them very close in height, and that's why I hate to say that then it became second, because if Mount McKinley is like this in Alaska, it may have several mountains real close to it that are taller than Whitney. So I don't know. I haven't seen the contour map of Mount McKinley. Okay. But anyway, this is the Mount Whitney Range in California. And here's the contour map of it. Okay? Now, just to get an idea of what's going on here, where you see the contour lines are closest together, that's the steepest part. And they're getting very, very steep. And I think, I'm not absolutely certain, this is the ridge line here. I can't tell that looking at this, but I believe that probably is the case. Okay. Now what your contour lines are these lines here. And usually the darker one is every, so if this was 20, 40, 60, 80, 100. So that would be a span of 100. I'm guessing feet, but I don't know that for sure, because they don't really specify here. So that would be the contour map. Okay? Notice that the lakes, that you have little pockets of lakes down here where glaciers probably melted and left. Those are all fairly close to that. I mean, they are obviously on the same contour, because otherwise the water would be spilling one way or the other. So those are always fairly close to the same. They are the same. Your peaks, it's really hard to tell what's going on here unless there's a kind of a flat area on the backside of this, which I would be supposed to be the case, because it looks like the contour lines are getting much further apart there. But here they're very steep on this side and that side. Okay? Then they flatten out as they go down. And you see there is a hill over here. My guess that's this one here. See, an individual hilltop is going to have close because the contour lines close around that. Whereas here, they don't. They close for a little bit, and you just can't see it here. But if you go this way, they map out the sides here because you see you got continuity all through here. That just can't make out this here. They just got too many things drawn too closely together, and then someone marked it. But that would be how a contour map would look. It shows elevation and also depression, like the lakes and things. Okay. Now, let's see what we can garner from this. Okay, now we're getting closer to what we're really going to be dealing with. What are we talking about when we talk about average rate of change? Now, they've got a block in the book they don't have here. Average rate of change is change in elevation. They call it altitude for change of horizontal. So rise over run. Only our run now is two-dimensional. You can run x-wise, y-wise, or anywhere in between in that white plane, but your elevation is a z. Okay? Now this is a stylized example, so a very regular geometric shape here, and they say the contour level is 0.8 of a kilometer. Okay? So that would be and the horizontal scale, that distance there would be 2 kilometers. Okay? So this distance here is that's 2 kilometers horizontal, whereas you're going up 0.8 for each one, so that'd be 0.8, 16 tenths, and 24 tenths. So 2.4 kilometers up for every 2 kilometers you run. So that's a really steep incline there, and that's going from P to Q. And you see it would be. As you get further down, then the steepness levels out as the contour lines get further and further apart. So these are the closest space. That means that's where the steepness is happening in grades. All right, here's supposedly a real life type example of that. Notice it's not a regular circular or elliptical pattern here. It wanders around some. Okay? So here we have the contour interval is 50 meters. So this is 1,000, 10, 50, 11, 11, 50, 12. And then we have to get one more. Those are elevations, areas of equal elevation. We call them isoclines. Okay? Your AB distance here is horizontal distance is 200 meters, exactly twice that. Shown here, AC is 400 meters horizontal. Okay. Now, contour interval is 50, so this is the difference here in elevation of 100 over 200, so that's a 1 to 2 slip, 1.5 slip. Whereas this one, on average would be, you still are only crossing 2 contour at 50 meters, so it's again a 100 meter difference in elevation, but now your horizontal transit is 400 meters. So that would not be nearly as steep on average going this way as it was this way. Now, of course, it may be very steep here and then very, very flat here, or relatively flat there. So you can't say it's always not as steep, but generally it's not as steep. And that totally shows here too. Here's point A, and you go to B, that's a pretty steep climb. Go to C, at least it's not as steep here for a way, but it may get steeper right up there. D, however, you're just following the contours, so there's no elevation change at all. You're walking on a fairly level path. And you zig and weave around a little bit, but vertically it's level. Okay. Now, why are we talking about all this? Well, that's leading up to example 8. Okay. The average rate of change depends on direction. Okay, just as we saw in the last one, the rate of change from P to Q here was 2.4 to 2, or 12 to 10, or 6 to 5. Okay? I think that's right. Okay? Whereas that one, the elevation change is still the same, 100 meters, but they're taking far longer time to get there, and it's an easier climb as well, so they're really having a good time. It's just not as steep. Okay? Now, so the average rate of change depends on your path. Okay? It says compute the average rate of change. I've lost it there. Compute the average rate of change from A to B and C to B. No C to D. Okay. From A to points B, C, and D. And the B part. Okay. That's going back to this one. Sorry. Compute the average rate of change from A to points B, C, and D in this figure. We really already did it. Well, at least for part of it. Or in this part. From A to B, that's the difference of 100 meters difference for every yeah, 100 meters for every 200, so that's the 1 to 2 average rate of change. This one would be change of 100 meters for every 400 meters, so that's 1 to 4. So this would be an average of 1 to 2 slope, 1/2 slope, 0.5 slope. This would be an average of 0.25 slope. Okay. Also, contour interval was 50. For vertical change was 100 in both cases. Okay. And D, the average rate of change is 0, because that's on the same contour, so your vertical change is 0, so your horizontal change, who cares what it is slope is still 0. Okay. So that was the why have they got this wrong? Oh! This is a different figure. I thought this was, okay, sorry. The left-hand figure is 16A. They don't show 16B. In our book, it's just totally different. It's not the right-hand side, you have to look at that. They labeled them the same, but they're different. So that's why the book was getting different answers from what I got. Okay, but you don't have a book. Okay. Well, I'm not going to change it. What I was saying was right there. It doesn't match in the book because they were looking at a different figure from the one I was. So we'll leave that alone there. Okay. All right. When we walk up a mountain, yeah, all right, the incline at each moment depends on the path we choose. If we walk around the mountain, our altitude doesn't change at all, or negligibly. Okay. On the other hand, each point there is steeper. At each point there is the steepest direction in which the altitude increases most rapidly. Okay. On a contour map, the steepest direction is approximately the direction that takes us to the closest point of the next highest level curve, and we say approximately because the terrain may vary between those level curves. The path of steepest ascent is the well, okay. I think these will be all right to look at. Let me see if they're just way too small for me to picture them here.
When does calculus come into play?
I'm sorry?
When does calculus come into play? I mean, how do we get calculus from this? Okay,
that's what I'm getting to. And that's why I'm wondering why it's taking them so long to get there. Is this concept of steepest ascent, the very thing we're talking about here. Now, if you happen to be at this point there, the path of steepest ascent is not going to be that way. See how long it takes you there or here. Is the one that's closest to being perpendicular here and there. It may not be exactly, but it's the one that comes closest to being perpendicular to this next step. If you're here, it's closest to being perpendicular there and there. Here, closest to being perpendicular there and there and there. So it's the shortest distance to the next contour. Okay? That's what we mean by the vector pointing approximately in the direction of steepest ascent. It's the shortest vector you can draw from that point to get to the next line. That's the steepest ascent. Okay? Now, surely if you had started somewhere else, like right here perhaps, you have very steep ascents on every one of them. Not the steepest here, but you have the very close to the steepest ascents on every one. This one, this is showing you the same thing. The shortest distance between this point and the next curve is going to be the one closest to being perpendicular to each other. Closest you can. And that would be the steepest ascent. Anywhere else from this point, you're going a longer horizontal distance for the same vertical distance, so that has to be steepest. And that would be steepest here, that's steepest here, that's steepest there. So it's not always the same thing. So you can't say what's the steepest between here and here. If you drew that, it would be the steepest on this part or this part. So you usually go between each two. But obviously this is not steepest here, here, here. That would be a more gradual route. But then look how much further you went to get there. But that's not necessarily bad. Have you ever heard of a sport called orienteering?
No.
Okay. It's a sport that they give you, someone goes out and sets up out a route. It's usually out in thick woods, usually a great deal of mountains and hills and valleys and canyons and everything else. Someone goes and just sort of arbitrarily sets a route, and you have to go from this one to that one to this one to that one. So you're not traveling necessarily in a straight line ever. And you may actually cross this way here and later cross this way, you know. You don't go to the same station twice, but you have to hit all the stations in the right order. Okay? And what you do, you're given a map, a contour map, that shows the contours, and it shows you the locations of these stations in their proper order. And they give you a compass. And they say run, okay? And you're supposed to go as fast as you can. Now, if you had a very steep canyon, maybe that's the closest point between these two, but it's probably not the best route because you're going way down and then way back up. If the canyon levels out here, you might be better to go this way and that way, and you actually, horizontally, you go a greater distance, but when you count vertical in it, you're in a terrible mess, okay? So, we had it's a European sport mostly, though America does have a team. We had a kid that lived with us one summer, and that was his sport, was orienteering. And not one summer, 1 year. That was his sport, orienteering. He's actually Italian, but he was born in the U.S., so he's a U.S. citizen and an Italian citizen. And he actually is on the U.S. team because he's so good at it. He would be average in Europe, but he's really good in the U.S. So he's on the U.S. national team. And he's a real sharp kid too. He's working on his PhD right now, but still running orienteering. Okay. So, I hope we're going to get to the answer to your question now. Just a couple of more things. You don't have to have just a three-dimensional thing. If you have more than two variables, now you're not talking about, okay, if you have two independent variables and one dependent variable, then you have contour curves, okay, as you're going up that independent variable. If you have three independent variables and you're going out from that, now you have contour surfaces. Now this would be contours around a single point, and these are all spheres. These are concentric spheres. But look at the curve. They're obviously alpha of x, y, z is x squared plus y squared plus z squared. These are your three independent variables, three this time, one dependent variable, your z, your L function, not z. Z is in one of your independent functions. So people know about this, use it and stuff, but how do you ever map whatever your alpha is there? You can't. You only have three dimensions and two, so you use x, y, and z, and then your alpha is doing something from there, pointing out, pointing in, pointing out, whatever it is, but it's based on the spheres. So when this is zero, of course, all of this is zero, you have a center. Then this can't be negative because each of these are positive, you add them together. So when this is a positive value, then you could have any number. You have a three-dimensional shape around that. Okay? Now, this is the last slide in this section. Thank goodness. Okay? All right, and I'll start over here, I think. All right. This is stuff we've done before. I think this is oh, and by the way, they don't always have to be physical. Like I was talking isoclimes, where you're measuring equal elevations, and those are your curves. Okay? I mentioned, I think last time, you can have isobars, which is areas of equal barometric pressure. That's what gives you your high pressure centers, your low pressure centers, your fronts, and things like that on a weather map. They mentioned here I can't think of the name of it. Therms, isotherms. That would be elevations at equal temperatures. Okay, not equal heights, but equal temperatures. So if you're over a body of water, probably the isotherm will go down because your temperature, well, that would be the same temperature. Actually, it may actually go up because. But anyway, you can have ISO just about anything. Anything that you're able to measure. Okay, this is the example 9 part. Describe the level surfaces of g of x, y, z, when that's x squared plus y squared minus z squared. Okay. What you have here are surfaces that are dependent on all 3 variables. Okay. Let's just see. When C is something greater than 0, a positive value, then that's your value here. This G function is some positive number. What that tells you is x squared plus y squared has to be greater than z squared. Okay? Well, what is that describing? X squared plus y. So let's just take g equals 0. That would be this case right here. If that were the case, x squared plus y squared would equal z squared. If this was 0, then as you go bigger and bigger with x, y, your z would also have to be getting larger, because if that were equal to 0, when x squared plus y squared is getting larger, z has to be getting larger too. Okay. Now, for c greater than 0, you have you remember what that shape was called?
The circle thing?
Or what?
Some of that whole entire shape? Or
Yeah. No, the
no, I can't.
okay. The horizontal traces are ellipses, okay? And this is, the vertical traces are hyperbolas. So this is a elliptic hyperboloid of one sheet. Remember? I think that's what it's called. Let me make sure I'm not saying it wrong. Okay. When C is equal to, when this G is equal to 0, then this thing's equal to 0. That means x squared plus y squared is equal to z squared. And all those are positives, so the only places that's going to be true is at the origin. 0 squared plus 0 squared equals 0 squared. Okay? So that is a cone. Okay? Okay? Now, the next two this next one here is a elliptic hyperboloid of 2 sheets. Okay? You have one. The cone, you cut it in 2, and if you keep moving out, this one C is less than 0. Well, let's go back and see what our equation looks like then. Whoops. Hit the wrong key again. I keep doing that. Okay. if I'm not paying attention to what I'm doing. Okay, here's the equation. All right. When C is less than 0, then G is less than 0. What that says is Z squared is greater than X squared plus Y squared. So your Z's are greater than the X squared plus Y squared. X squared plus Y squared equals 0. You can't have C less than, negative then, So it's a elliptic hyperboloid of 2 sheets. Okay? Now, this time I'll try to hit the right key. Now, what do we have here? This is hyperboloids, okay? This is basically showing all three at once. The blue is an elliptic hyperboloid of 1 sheet, the cone is the yellow, and the green is the elliptic hyperboloid of 2 sheets. Okay? Okay. And that's it for the thing. Okay. Let's see. It's probably going to be the one. No, that may be better. Yeah. All right. Do you want to do preliminary questions?
Sure.
Okay. What is the difference between a horizontal trace and a level curve? Horizontal trace and a level curve. And how are they related? Okay. You sort of have to go back to the very beginning. This was one long section, and there was very little, like you said, calculus in it. It's just sort of setting you up so the rest of the chapter makes sense. Let me see if I can find the horizontal traces here. Here's vertical traces. Where's your horizontal trace? Okay. On the bottom, oh, you don't have this book. Horizontal trace at some height C is the intersection of the graph with a horizontal plane Z is equal to C, consisting of the points x, y, f of x, y, such that f of x, y is equal to C. So that's where that's that. Your level curve is that horizontal trace projected down onto the xy plane. So this is it. These are your horizontal. These are your level curves. Horizontal traces are these. When you project them down on the xy plane, that's your contour path. Those are your level curves or contours. Those are your level curves. Okay. Okay. Let's make sure that they're answering it the same way we are. So that's 14.1. The same shape but located in parallel planes.
Oh, which one?
That's the thing. They don't really answer that well. The horizontal traces are located in parallel planes. The level curves are projected onto the XY plane. Their definition in the back is really poor. Okay. I wonder if it's even the right question. It's supposed to be. I'm guessing they changed the preliminary question in this edition but left the answers from the previous edition. I don't know. Let's do number 2. Describe the trace of f of x is equal to x squared. Ooh, wow. Okay. I want this one. Describe the trace of f of xy. Is my pen? No, my pen's not right. Okay. F of xy is equal to x squared minus sine x cubed y in the xz plane. Okay? Describe the trace of that in the XZ plane. Okay, where's the XZ plane? What's true about the XZ plane? Y is 0, exactly. Okay? Now, if y is 0, then sine of 0 is 0. So it doesn't matter there. So what you have in the XZ plane, your trace, your vertical trace there, would be the function c is equal to x squared. That would be a parabola in the XZ plane, opening up around the z-axis. Yeah. Okay? So that would be a parabola in the z-axis. Okay? Let's make sure that's how they say it here. The parabola z is equal to x squared in the XZ plane. Perfect. Now, number 3. Is it possible for two different level curves of a function to intersect? Two different level curves of a function to intersect? No, you're absolutely right. It can't happen. Because if it's a function, you can't have two y values or z values for the same xy point. Okay. Okay. Number 4. Describe the contour map of f of x equal x, f of xy equal x, f of xy equal to x, that's all, with a contour interval of 1. Okay. Describe the contour map. F of xy is equal to x. Okay? Now, let's say that x is equal to 1. Okay? Then f of xy would be 1. Okay? Meaning your z would be 1. Doesn't matter what your y is. So whatever your x, if your f of xy is 2, then z is 2. Right? That's what it's saying. I mean, yeah. If x is equal to 2, then your z is equal to 2. Doesn't matter what the y is. Okay? So at 0, it's 0. At 1, it's 1. It's 2, it's 2, it's 2. So basically what it is the plane, the entire plane that, okay, that's my origin. X-axis, y-axis, z-axis. Okay? So picture the line, the 0, 0, 1, 1, 2, 2, 3, 3, 3. Okay. We used to call it the identity function. Okay, and it sort of is, but now it's an entire plane that's the identity plane. See, y, it doesn't matter what value it is, but whatever the x value is, that's the z value. So that's the plane that cuts this at 45 degrees. Okay. Right? Yeah. That's it. Okay? And it says, describe the contour map with a contour interval of 1. So you're going up 1. So if you're mapping onto the xy plane, that's a contour map. At 1, there would be a straight line here, a horizontal line, a vertical line in the xy plane. X equal 1, x equal 2, x equal 3. So it would just be that. Never crosses the y-axis except the x equals 0, and then it's all along the y-axis. All right, let's see if that description equals this one. Oh, wait, I'm sorry. That's number 4. The vertical lines, x equals c, with a distance 1 unit between adjacent lines. Yeah, vertical lines. If in the xy plane, there would be vertical lines, 1 distance, 1 apart. Exactly. That's what we said. Number 5. How will the contour maps of f of xy equal x and g of xy equal 2x with contour interval 1 look different? Okay? projected onto the XY plane, this would be vertical lines 1 apart, the other would be vertical lines 1/2 apart. Right? Yeah. Okay. I think that's what we're talking about. Contour map of g of xy equal 2x, the distance between the two adjacent vertical lines is 1/2. And we already discussed. So homework exercises do either 1 or 3 or both. Any of the odds 5 through 11, either 13 or 15 or both. Any of the odds, well, let's say 17 or 19 or both. Any of the odds 21 to 25, do 27. Any of the odds 29 to 35. Do either 37 or 39 or both. 41 or 43 or both. 45 or 47 or both. 49 or 51 or both. And either 53 or 55 or both. You don't have to do all those, but try to do some of those, and that'll give you a pretty reasonable expectation. All right. Go through that. Let's go to the next section. And it seems like it's taking forever to get to the calculus of this, but we're going to get closer now. I don't know why this is opening. Everything is so stinking slow here. Now finally it's responding. Okay. And we'll do from current slide. Okay. 14.2 is limits and continuity in several variables. Now remember how we did limits and continuity in two-dimensional calculus. Okay? Continuity was there's no breaks anywhere, no holes, that kind of stuff. There's just continuity. Okay? Along X. No, your Y's didn't deviate suddenly when you increased in X. Okay, that's continuity. Limits then would be as X is approaching something, what's Y approaching? If it does have a limit, what is it approaching? All right, well in 2 dimensions, you aren't just talking about going along the x-axis or a horizontal axis. What you're talking about now is if you have 2 independent variables and 1 dependent variable, then what you're talking about is an open disk, okay? Because you do have, and it doesn't have to be a circular disk, it's just some sort of shape, okay? And that would be all points, and this is to talk about continuity, all points within some radius of a given point, and all your xy's have to be within that radius r, okay? The point P is given, and the disk would be the open disk. Now when it says open disk, that does not include the boundary. It may or may not be included, but usually not including the boundary, okay? And that would be represented by B of PR, P being the center, the point at the center, and R being the radius, and you're everything up to but not including that radius. So that XY would be in, this would be in, this one would not be in, that one on the boundary would not be in, okay? Now, there's also another one that's D star, and what that means, it excludes the point P. P doesn't have to be in that domain, it's just everything around P. So the open disk D of PR, where P is the point at the center and R is the radius around that point, consists of all the points XY at a distance less than R from that point P. Not equal to R, that would include the boundary, but less than R. It does not include the boundary circle, okay? And D star doesn't even include P, but everything else. Okay. Now, this at least is sounding a little bit more like calculus, talking about limits and continuity and that kind of stuff. So here's our definition of a limit. Let's suppose that you have some function f of x, y defined near some point p. That could exclude p, but near some point p, which is ab. Now, the limit of this function of xy as xy approaches that point b, which is ab, you could call it that, then the limit of that is L if for any epsilon greater than 0 there is a delta greater than 0 such that the difference between f of xy and L will always be, the absolute value difference, will always be less than the epsilon for all xy's within that disk around point P, AB, okay, and some radius delta from it. So delta becomes your radius now. So if you're within this, so this is continuous, the limit exists if there, for some epsilon greater than 0, you can find the delta. There exists some delta so that the xy that makes this true will be within that open disk, excluding point P of radius delta. Okay, that all your xy would be in there. So that's saying no matter how small you choose this, you can find some delta that makes sure that this is true for those xy's. Okay? Just like we did before, the limit exists for any epsilon. Whatever epsilon you choose here, you can find the delta here, you can guarantee the be between there. So this is saying you can find the delta, some radius here, guarantee that all your values, f of xy minus L, are within the epsilon delta. Okay? So the epsilon's on sort of like the z-axis, and the xy are within some delta of p. Okay. Sort of seems like the same concept. Okay. Is this example 1? I can't tell. It's just too little. The writing is just pathetically small. That's just the second line of your thing. Definition of limit. Okay. That was the second line of what was up there. Okay. Now, I just noticed the limit is defined ever so slightly different here, but it basically is saying the same thing. And this is the second line of that. Okay. So we're not at example 1 yet, but I think this one now is example 1. Let's see if we can zoom in. Okay. Show that the limit as xy approaches AB as x approaches A, and the limit as xy approaches AB of y is equal to B. Okay. Man, this seems like it's really bizarre. Okay. This sort of shows it, but it's not exactly sure, but exact, but show that the limit, let me write this down, of course it's going to lose the blow up here. Here's what we're asked to show. Goodness, this pen's hot, it's been lying in the fan for that. The limit, and again, this kind of stuff, it seems so obvious. It seems like, why would you even mess with doing that? The limit as xy approaches the point P, okay? And by the way, they tell us that P is the point AB, the limit as the xy point approaches the point P, which is indeed AB. So let me actually write it that way. I mean, this is so, the limit of x as the point approaches that, I mean, duh. What's the limit of x as xy is going to AB? Well, obvious, x is going to A, isn't it? So that's what it is. It's equal to A. And you say, what is that teaching me? I mean, the B part of this is just as, to me, is just as bizarre to ask it as xy is approaching AB. The limit of B is, limit of y is going to be B, okay? As xy is approaching B, the limit of xy of y is getting closer and closer to B, okay? I don't know. I don't know why they do it, except if you have to establish this at the very beginning, fine. And they go through the formal definition and everything else. It just seems like it's so obvious, why even mess with it? Okay. And I'm trying to see if there's any, yeah. If this is in one variable, as x approaches A, the limit of x as x approaches A is A. I mean, there it is, okay? That limit would be that, okay? In two variables, x, y, x can approach A in many ways. Here it can only approach A twice, two ways. Here it can approach A in many ways. If here's your point AB down here, here's your curve up here with that point AB. Well, notice they put a little hole there. That means that P does not have to be on that surface. That's that piece, the disk with a star by it. P does not have to be defined at the hole, but everywhere else. X could be approaching A. See, here's x equal A, it's right there. So X could be approaching A this way or that way, or it could be approaching A, it could be approaching A any kind of a way, okay? And there's just tons of different ways that the point xy can be approaching AB. Okay, but if x is getting closer and closer, if xy is getting closer and closer to AB, x has to be approaching A. Okay? No doubt about it. Okay? So your point xy is in this domain of radius delta as xy is getting closer and closer to the point AB, wherever, however that shape is here, that limit exists if that's the case. So it is approaching that. Now, if this had been a surface that went up like this and went up like this and never got there, no, then it couldn't. Okay, that would not have a limit. But this one, if the limit exists, that would be the case. Okay. Now, all right. This time we have a plane here. I guess this is the second part here, the illustration of it. Now here, remember the star here means this disk here that you don't have to include the point P. So that could be an open circle there and could be an open circle up there. And we have the alpha of x, y minus b is y is approaching b less than epsilon if y minus b is less than delta. Well, if this is a plane, then that's a direct linear relationship. Delta would be epsilon. Therefore, the limit is that y approaches AB of y would be b, because xy is going close to AB, the y is going close to B. X is going close to A, y is going close to B. So it's kind of nuts. And here finally we hit some limit laws. And these will look, hopefully, and seem familiar. For some reason my cursor has decided not to show up anymore. So I'm going to do it this way. That way. Okay. All right. Let's assume now that the limit as xy approaches p of f of xy and the limit as xy approaches p of g of xy both exist. Both of these functions have limits as xy approaches that point p. Okay? The sum law says that the limit as xy approaches p of the sum of two functions is the sum of the limits of those two functions, which is exactly, I hope, what we would expect it to be. The limit of a sum is the sum of the limits. Constant multiple law, you should be really familiar to you by now, for any number k, that's any real number k, the limit as xy approaches p of that number k times f of xy, that limit does exist, is equal to k times the limit of this thing that we know exists. Okay? So it just, the limit as xy approaches p would just be k times whatever that limit is. Okay? If you're multiplying out everything in functions like k. K could be a huge number or a small number. Okay, the product law. The limit as xy approaches p of a product of two functions is sure enough the product of the limits of those two functions, which we know exist. And the quotient law, if the limit of xy approaching p of g of xy is not equal to 0, then the limit as xy approaches p of f of xy divided by g of xy is the limit of f of xy as xy approaches p divided by the limit. So the limit of a product of a quotient is the quotient of the limits, as long as that limit in the denominator is not 0. Then it's defined. Okay. Now continuity. This sometimes it's an easy thing sort of to picture, but sometimes a little bit harder to define. Okay? A function f of xy is continuous at p of ab, p equal ab, if the limit as xy approaches ab of f of xy is f of ab. Okay? So it is pretty simple to state. We say that f is continuous if it's continuous at every point ab in its domain. So, if you had a function here that was going up, say, picture a volcanic mountain, and as the f of a, this is point AB is going to be right in the center of the crater, okay, of that volcano. And as you go up, then either you have the top blown into the air, or the top already blew in and then, or lava came up and then sunk down, that the limit of this function here, the shape here, if the actual f of AB was up here or down here, anywhere other than there, then that is not a continuous function. And obviously it wouldn't be. You'd have a hole in this and then another point here, or somewhere else. So that wouldn't have a limit. But for every f of A, for every point AB, or xy, that f of xy is equal to f of AB, so it's exactly where it would be pointing to, then yeah, that would be a continuous function. In other words, there's no holes, no gaps, no separations, which is exactly what we would have. All right. And here my cursor is not showing up again. Okay. Now, this is figure 4, which I think is example 2. show that f of xy, is equal to 3x plus y over x squared plus y squared plus 1 is continuous. Okay? Then evaluate the limit as f of xy approaches 1, 2. As xy approaches 1, 2. All right. So we need to first show that's continuous. Well, one thing that lends to continuity, that denominator can never be 0. Okay, anytime you have, and then everything else is no problem here. As long as the denominator is not 0, that's going to be continuous. Okay? Because no matter what point you choose, you're going to be able to evaluate it, and it'll be connected to the other points. All right, the second part of that, which I'll have to do with this shrunk down here, it says evaluate the limit as xy approaches 1, 2, I believe it was, wasn't it? Yeah, of f of xy. Where f of xy is 3x plus y over x squared plus y squared plus 1. Okay? So what would you do to evaluate the limit? Second? I can't hear.
I'm sorry. I don't know.
Plug in the values.
Yeah, please.
Okay? So 3 times 1, see the x is approaching 1, that would be 3 plus 2, because y is approaching 2, right? Over 1 squared would be 1, plus 2 squared is 4, plus 1. That would be 5 over 6, right? Yes. Yep, that's exactly what they got. Okay? And basically that goes by the quotient rule. That the limit of the quotient is a quotient of the limits as long as the denominator is not 0. Okay. So example 3, are we going to have time for it? Evaluate the product function. I think we will. It's so simple. I don't think there's a graph, so let's just do it. The limit as xy approaches 3, 0, no, I've lost it. Yeah, xy approaches 3, 0. Of x cubed times the sine of y over y. Well, that would just be a product, wouldn't it? So that would be the product of the limit, and then you don't even need the point anymore. X approaches 3 times the limit of x cubed times the limit as y approaches 0 of sine y over y. Now, that almost looks like it'll be a problem, except we know what that limit is. Well, what's this one? The limit is x approaches 3 of x cubed.
18.
Nope.
Oh, 27.
27. Okay, 27. Now, do you remember what the limit of sine 0 over 0 was? Sine y over y, sine x over x.
Sine y over y.
Yeah. What the limit was as y approached 0? That's exactly 1. So this will be 27. Okay. And that's exactly what they got to. Okay? Now you could have just plugged in the way we did without doing the breaking in the product, but yeah. I think to separate the sine y over y. All right, I think we're going to have to stop there because we've just run over, and we will pick up with theorem 2 next time. Okay. It's taking way too long. But let's end this. Any questions before I end it?